Chapter 28 is taking a look at something known as special relativity. This is where science gets a little bit weird. So, we're going to start out with section 28.1, events and inertial reference frames. This will give us some guidelines, some various words and terms for the ideas and the concepts ahead. So first, an event is a physical happening that occurs at a certain place and time. A light flashes, right? Cool, that was an event. That happened at one instant in time, at one place, right? Here, right? To record this event, each observer, like myself observing this flash, uses a reference frame that has a coordinate system, maybe relative to me. I can measure this distance, and a clock, right? I could be looking at the time and say like, oh, cool, I know that that happened right at this instant in time. Now, each observer is also going to be at rest relative to her own reference frame. So it's a little more obvious when you're staying at home. Okay, cool, you're at rest, sweet. But it's also true if you're riding the bus somewhere or in an airplane. Relative to the airplane, you're sitting in your seat, you are at rest. So that's an important idea, and it actually will look like if you're in the plane, and if you don't know that you're moving, it looks like everything else is moving around you. So that's another aside, just giving a little foreshadowing. And then specifically, an inertial reference frame is one in which Newton's laws of inertia is valid. And what we effectively need for that is that it's not accelerating. We're just going to look at reference frames that are traveling at a constant velocity, like your airplane when it's cruising through the air. All right, so looking at an example of this, you could have a space shuttle that's getting ready to take off. And so as it's taking off, that can be observed by multiple observers. You can have an observer that's in an Earth-based reference frame. They're standing on the Earth, and relative to the Earth, they are not moving. They have a clock and a reference frame, so they can say that it occurred at this instant. You could also have an observer that's in an airplane. They have their own clock, their own reference frame, and they might observe a slightly different time than the Earth-based reference frame. All right, so we could even have an observer on the space shuttle itself, right? But in general, we're going to have reference frames that are on a non-accelerating, and the space shuttle, as it's taking off, is definitely accelerating by quite a bit. So probably not have an observer there. Okay, 28.2, the postulates of special relativity. There are two basic postulates, and these seem relatively simple, but they have pretty important implications. So the first postulate is the relativity postulate. It says the laws of physics are the same in every inertial reference frame. So as long as your reference frame is not accelerating, as long as it's going at a constant velocity, the laws of physics should hold. You shouldn't see any weird effects that don't match what you'd see if you were just standing on the ground. The second is the speed of light postulate. This says that the speed of light in a vacuum measured in any inertial reference frame is always that same value of c, no matter how fast a source of light and an observer are moving relative to one another. This is something that at first glance is like, sure, light just travels at the speed of light, but it gets a little weird when you start thinking about it and comparing it to other velocities. For instance, if someone in the back of a truck throws a ball, say they throw the ball at 8 meters per second, the truck is moving at 15 meters per second, then if you're on the ground, what you effectively see is that ball is moving not just with 8 meters per second, but 8 plus 15 meters per second, or a total of 23 meters per second of how fast that ball is moving towards your face. Very quickly, right? Because it has the additional boost of the truck that's going in the same direction. If instead the person on the truck turns on a flashlight and shines that light, then the person shining the light would see it moving at the speed c, the speed of light, 3 times 10 to the 8 meters per second. But even though the truck is moving in that same direction, the ground-based observer on Earth would observe the exact same thing of c 3 times 10 to the 8 meters per second. So the observer on the Earth as well as on the truck would both see the same speed of light. And this has really strange implications on how it affects time and distance or length. We'll see those in the next section, so stay tuned on that. But what you want to hold on to is the speed of light is our only constant. Everything else is going to change.